Far out beyond Neptune, drifting in the frozen darkness of the Kuiper Belt, there's a tiny world that shouldn't exist. Meet Eris, the dwarf planet that shattered our understanding of the solar system. When astronomers first spotted this enigmatic object in 2005, it sent shockwaves through the scientific community. Here was something almost the same size as Pluto, yet somehow denser, brighter, and far more mysterious. Its discovery forced us to rewrite the textbooks, demoting Pluto and redefining what it means to be a planet. But that was just the beginning. Eris isn't just another icy rock at the edge of our cosmic neighborhood. It's a riddle wrapped in frozen nitrogen, a place where the laws of physics seem to twist in ways we can't yet explain. What makes Eris so bizarre? For starters, it's unnaturally reflective, shining brighter than fresh snow, as if its surface were coated in cosmic glitter. Then there's its mind-bending density, suggesting hidden depths beneath that dazzling exterior. Some researchers whisper about the possibility of underground oceans, kept liquid by forces we don't fully understand. Others point to its peculiar orbit, tilted at a sharp angle compared to the rest of the solar system, as if Eris were trying to escape the sun's grasp entirely. And let's not forget the whispers of unusual geological activity on a world so small and distant, where sunlight is barely a memory. How could such a place defy expectations so spectacularly? That's exactly what we're here to uncover. In this journey, we'll explore 25 of Eris's most baffling secrets, from its mysterious bright spots that shift over time to the eerie possibility that it might not be alone out there. Each mystery peels back another layer of this cosmic onion, revealing just how little we truly know about the edges of our own solar system. So buckle up. By the time we're done, you'll see why Eris isn't just a footnote in astronomy. It's a challenge, a dare from the universe itself, waiting for us to solve its puzzles. And trust me, the deeper we go, the stranger it gets. Eris doesn't just drift through the outer solar system, it practically dances, flaunting a path so erratic that astronomers first thought it might be a visitor from another star. Most objects in the Kuiper Belt move in relatively flat, circular orbits, like marbles rolling smoothly along the edge of a plate. But Eris, it swings wildly around the sun in a stretched, elongated loop, tilted at a jaw-dropping 44 degrees. Picture a car speeding down a highway, then suddenly veering up a mountainside. That's the kind of cosmic detour we're talking about. What could possibly cause such a dramatic deviation? One leading theory points to Neptune's gravitational tug. In the early days of the solar system, the giant planet may have slung Eris outward like a stone from a slingshot, warping its orbit in the process. But here's the twist. Simulations show Neptune's influence alone can't fully explain Eris's extreme tilt. That's led some scientists to suspect a more violent past, a catastrophic collision with another large object, one forceful enough to knock Eris off kilter for good. Imagine two icebergs smashing together in deep space, sending one careening off at an impossible angle. The impact would have been apocalyptic, reshaping Eris's destiny in an instant. Yet even these explanations leave gaps. Some researchers argue Eris's orbit hints at something even stranger, the ghostly pull of an unseen ninth planet lurking in the solar system's shadows. This hypothetical world, 10 times heavier than Earth, could be yanking Eris and other distant objects into their bizarre paths. It's a tantalizing idea, one that turns Eris into a celestial breadcrumb, pointing the way to an even greater mystery. Whatever the cause, Eris's defiant orbit makes it a rebel among icy worlds, a maverick that refuses to follow the rules, and that's just the first clue in a much larger puzzle. If there's one feature of Eris that stuns astronomers more than anything, it's the way it gleams like a diamond in the cosmic dark. Despite being 3 times farther from the Sun than Pluto, this distant world reflects a staggering 96% of the sunlight that hits it, making it one of the shiniest objects we've ever found in the outer solar system. To put that in perspective, Earth's moon, bathed in direct sunlight, only reflects about 12%. Even freshly fallen snow on Earth can't compete with Eris's brilliance. So what's coating this frozen world to make it so blindingly bright? The leading suspect is methane ice, which forms a thin, mirror-like frost on its surface. When methane freezes in the vacuum of space, it creates crystals far more reflective than water ice. But here's the catch: methane shouldn't last this long on Eris. At its distance from the Sun, solar radiation should have broken down any surface methane into dark, reddish sludge over billions of years. Yet Eris still sparkles as if it were freshly polished. Some scientists speculate that geologic activity might be replenishing the methane, with pockets of the gas bubbling up from below and refreezing on the surface. Imagine geysers erupting in slow motion, their plumes freezing instantly into glittering frost. But methane alone might not explain everything. Infrared observations suggest the presence of nitrogen ice mixed in, which could create even higher reflectivity in certain conditions. There's also the possibility of exotic ices we've rarely seen in nature, like ethane or propane, forming a bizarre cocktail of frozen gases. And then there's the wild card. Some researchers propose that Eris's shine comes from something called tholins, complex organic molecules created when radiation bombards simple ices. These compounds usually darken surfaces, but under specific circumstances, they might arrange themselves into highly reflective structures. The more we study Eris's glare, the stranger the puzzle becomes. Its brightness isn't uniform. Patches of the surface appear to shift in reflectivity over time, as if hidden forces are actively reshaping its frozen shell. Could underground heat be causing localized resurfacing? Is some kind of seasonal process at work, or is there something entirely unexpected lurking beneath that dazzling facade? One thing's certain: Eris isn't just a frozen relic. It's a dynamic world hiding secrets under its radiant surface that challenge everything we thought we knew about the outer solar system. Here's a cosmic measuring contest that's been puzzling astronomers for nearly 2 decades: Eris versus Pluto. When Eris was first spotted, initial observations suggested it might actually be larger than Pluto, which played a major role in Pluto's infamous demotion from planet status. But as we've studied these distant worlds more closely, the answer has become anything but clear. The latest measurements put Eris's diameter at roughly 1,446 miles, just a hair smaller than Pluto's 1,477 miles. That difference, about 30 miles, barely the width of a small country on Earth. So why can't we settle this once and for all? The challenge lies in Eris's incredible distance and the quirks of how we measure objects at the edge of the solar system. Even with powerful telescopes like Hubble and advanced techniques such as stellar occultations, where scientists watch how Eris blocks the light of distant stars, tiny uncertainties in observation can throw off calculations by dozens of miles. There's also the complication of Eris's atmosphere, or lack thereof. Pluto's thin but detectable nitrogen haze can subtly distort size measurements, while Eris's more reflective surface might create optical illusions in telescopic data. It's like trying to measure 2 marbles from a mile away, one covered in frost, the other in fog, using only the flickering shadows they cast. But here's where it gets even more intriguing. While Eris might be slightly smaller in diameter, it's significantly denser than Pluto, packing about 27% more mass into a comparable volume. That unexpected heft suggests Eris could have a much larger rocky core lurking beneath its icy shell, or perhaps a different mix of materials altogether. Some researchers speculate that Pluto's puffier size might come from volatile ices that sublimate and refresh its surface, while Eris's compact density hints at geological processes we've never seen on other dwarf planets. The debate over which world is bigger ultimately comes down to how we define size itself. Is it pure diameter, total volume, gravitational influence? Each metric tells a different story, and Eris seems determined to keep us guessing. One thing's certain, this isn't just academic nitpicking. Understanding these discrepancies could rewrite what we know about how dwarf planets form and evolve in the solar system's frozen outskirts. And with every new observation, Eris reminds us that even the simplest questions like which one's larger can lead to profound cosmic mysteries. Circling Eris in the deep freeze of the Kuiper Belt, its lone moon Dysnomia moves like nothing else in the solar system. Most moons orbit their planets in neat, circular paths, staying close to the equatorial plane like satellites around Earth. Dysnomia, by contrast, traces a wild, lopsided loop around Eris, a 17-day-long dance that takes it far above and below the dwarf planet's poles. It's as if this moon is tethered to Eris by an invisible bungee cord, swinging unpredictably through space. The strangeness doesn't stop there. Dysnomia reflects light with an intensity that rivals its parent world, an anomaly for cosmic companions of this size. Typically, moons are darker than the objects they orbit, having been battered by eons of impacts that leave their surfaces pitted and rough. Yet Dysnomia gleams almost as brightly as Eris itself, suggesting it might be coated in the same mysterious reflective ices. Even more puzzling, the two objects appear to be tidally locked in a gravitational embrace far tighter than Pluto and its largest moon Charon, rotating in perfect sync as they hurtle through the void together. So where did Dysnomia come from? The leading theory points to a cataclysmic collision, a smash-up so violent it tore a chunk of Eris free, leaving the moon as a permanent scar of that ancient violence. This would explain the tight tidal lock and shared composition. But if that's true, why doesn't Dysnomia orbit along Eris's equator like Earth's moon does? Some researchers propose the impact was so extreme it sent Eris spinning wildly before settling into its current rotation, leaving Dysnomia stranded in this odd path. Others wonder if Dysnomia might be a captured object, a rogue Kuiper Belt body snared by Eris's gravity long after both formed. The capture theory raises its own questions, though. Dysnomia's reflectivity and apparent age seem to match Eris too closely for coincidence, as if they've shared the same deep freeze history for billions of years. And if Dysnomia were a captured wanderer, its orbit should be even more erratic than what we observe. This leaves astronomers with a cosmic whodunit one where every clue contradicts another. Perhaps the most tantalizing possibility is that Dysnomia isn't alone. Some models suggest Eris once had other moons, lost to gravitational tugs or collisions over time. If true, Dysnomia's odd path could be the ghostly imprint of those missing siblings, their influence still warping its orbit long after they vanished. One thing's certain, this tiny moon holds outsized secrets about Eris's violent past, and untangling its mysteries might just rewrite what we know about how dwarf planets and their satellites evolve in the solar system's farthest reaches. Eris doesn't just reflect sunlight, it throws it back with an almost defiant brilliance, outshining even the freshest snowfall on Earth. This stunning reflectivity, known as albedo, sits at a jaw-dropping 96%, making it one of the brightest objects in our solar system. For comparison, freshly fallen snow reflects around 90% of sunlight, while Pluto, Eris's closest rival in size, only manages about half that. So how does a world 3 times farther from the Sun than Pluto manage to outshine it so dramatically? The leading suspect is methane ice, which forms a mirror-like veneer across Eris's frozen plains. When methane freezes in the deep cold of the Kuiper Belt, its crystalline structure scatters light with remarkable efficiency. But this explanation comes with a glaring inconsistency. Methane shouldn't stay this pristine. Over billions of years, solar radiation should have broken it down into darker compounds, leaving Eris's surface stained reddish-brown, much like Pluto's. The fact that it hasn't suggests something is actively refreshing the ice, perhaps hidden geologic activity, like nitrogen geysers or cryovolcanoes, erupting sporadically to coat the surface anew. Imagine a self-polishing jewel constantly renewing its own shine in the void. Nitrogen ice could be another piece of the puzzle. Found in abundance on Pluto, nitrogen is even more reflective than methane under certain conditions. But Eris's extreme distance from the Sun makes this explanation tricky. At its frigid temperatures, nitrogen should be locked in an inert, glacier-like state, not actively resurfacing. Unless, of course, tidal forces from dysnomia or residual internal heat are churning the ice, keeping it fresh. Then there's the wild card, tholins. These complex organic molecules typically darken surfaces, but under specific conditions, they might form microscopic structures that amplify reflectivity. Picture a frozen labyrinth of microscopic mirrors scattering light in every direction. Some researchers even speculate that seasonal shifts, Eris's slow, centuries-long seasons, could trigger atmospheric collapses, dumping fresh frost across the landscape in cycles we've yet to observe fully. The real enigma, Eris's brightness isn't uniform. Patches of its surface appear to vary in reflectivity over time, as if hidden forces are at work beneath the ice. Could underground liquid reservoirs be bubbling up? Is there an unseen energy source like radioactive decay in its core driving these changes? Every answer leads to deeper questions, proving that Eris isn't just a frozen relic, it's a dynamic world challenging our assumptions at every turn. And until we send a probe to its distant shores, its radiant secrets will remain just out of reach. One of Eris's most confounding puzzles isn't just what we can see, it's what we can't. Temperature readings from this distant world reveal wild inconsistencies that defy the laws of thermodynamics as we understand them. Given its staggering distance from the Sun, Eris should be locked in a deep, unchanging freeze, with surface temperatures hovering around a bone-chilling -400 degrees Fahrenheit. Yet infrared scans reveal strange hot and cold spots scattered across its surface, some deviating by dozens of degrees from what models predict. It's as if this dwarf planet has invisible furnaces and iceboxes hidden beneath its glittering shell, flickering on and off in a pattern we can't yet decipher. So what could possibly be generating these bizarre thermal fluctuations? One possibility lies beneath the ice. Radioactive decay in Eris's rocky core might be producing residual heat, much like the geothermal activity that warms Earth's interior. But here's the catch: Eris is too small, according to conventional wisdom, to retain significant internal heat after billions of years. Unless, of course, its composition is far denser than we've estimated, with a core packed with unusually high concentrations of uranium, thorium, or other radioactive elements. Imagine a tiny world with the heart of a nuclear reactor, its decay process slowed by the cold of space but never fully extinguished. Then there's the atmospheric angle, or lack thereof. Most objects in the Kuiper Belt are too small and cold to hold onto substantial atmospheres, but Eris's reflectivity suggests volatile gases might occasionally sublimate from its surface, creating a temporary, whisper-thin envelope. When these gases freeze back onto the surface, they could release latent heat in uneven bursts, creating localized warm zones. Picture dry ice sublimating on Earth, but on a planetary scale, with invisible geysers of nitrogen or methane puffing out and refreezing in an erratic cycle. But the most tantalizing theory involves tidal forces from Dysnomia. Just as Jupiter's gravity stretches and squeezes Io, creating violent volcanic activity, Dysnomia's gravitational tug could be flexing Eris's interior, generating friction heat. The math is tricky. Their dance isn't as extreme as Jupiter's moons, but even slight flexing over billions of years might explain why Eris hasn't yet frozen solid. Some researchers speculate this process could even maintain pockets of liquid water deep underground, a cosmic equivalent of geothermal hot springs in perpetual darkness. The real mystery isn't just the heat, though, it's the patterns. Thermal maps show these temperature anomalies aren't random. They cluster in specific regions, as if following some hidden geological blueprint. Could Eris have cryovolcanoes quietly erupting slushy ice and gas? Is its crust fractured, allowing warmth to seep through like cracks in an igloo? Or is there something even stranger at work, a process we haven't yet imagined, rewriting the rules of thermodynamics in the solar system's frozen backyard? Until we send a probe to Eris, these questions will linger, proving that even in the coldest reaches of space, heat can still turn science upside down. In the frozen reaches of the solar system, atmospheres are fragile things, especially for small worlds like Eris. While its cousin Pluto retains a wispy nitrogen shroud that periodically swells and collapses with its seasons, Eris appears almost naked in comparison. This absence is baffling. Given its similar size and icy composition, scientists expected Eris to harbor at least a transient atmosphere, especially when its elliptical orbit brings it slightly closer to the Sun. Yet every observation suggests this dwarf planet clings to nothing more substantial than the occasional whiff of gas. The mystery deepens when we compare their histories. Both Pluto and Eris formed in the same frigid neighborhood, rich in volatile compounds like nitrogen, methane, and carbon monoxide, ingredients that should easily form temporary atmospheres when warmed by even the weakest sunlight. Pluto's thin envelope persists because its gravity, though weak, is just strong enough to keep these gases from escaping entirely. Eris, however, seems to lose them almost instantly, like smoke vanishing in a breeze. One key difference might lie in their surfaces. Pluto's mottled terrain, with its dark patches and sprawling glaciers, absorbs enough solar heat to sublimate ices into gas. Eris's mirror-like reflectivity, on the other hand, bounces away most incoming energy, leaving its frozen plains too cold to release substantial vapors. Then there's the question of mass. Eris is slightly smaller than Pluto but significantly denser, hinting at a larger rocky core. That extra density should translate to stronger gravity, enough, theoretically, to hold onto gases even better than Pluto does. Unless, of course, Eris's interior is sucking those gases back down as fast as they escape. Some models suggest cryovolcanic activity could be trapping sublimated ices beneath a thick, insulating crust, preventing them from forming a stable atmosphere above. Imagine a world where geysers spew frost not into the sky but into hidden underground chambers, locking gases away in a subterranean labyrinth. Another possibility is sheer bad timing. Eris's extreme orbit means it spends most of its 257-year journey around the Sun in near total darkness, where temperatures plummet too low for any ice to vaporize. By the time it reaches its closest approach, still farther out than Pluto's average distance, the brief window for atmospheric formation might be too short for telescopes to catch. We could simply be looking at Eris during its long cosmic winter, missing the fleeting summer moments when a thin haze might appear, but the most tantalizing theory involves cosmic collisions. If Eris suffered a massive impact early in its history, perhaps the same violent event that created Dysnomia, the energy could have blasted away any primordial atmosphere, leaving it stripped bare. Pluto, by contrast, may have dodged such cataclysms, preserving enough gases to maintain its delicate balance. Without direct measurements from a visiting spacecraft, we're left piecing together clues from afar, watching a silent world that refuses to reveal whether it's truly airless or just biding its time. The absence of an atmosphere isn't just a curiosity, it's a window into Eris's hidden dynamics. If gases can't escape, where are they hiding? If they do escape, why can't we detect them? Every unanswered question tightens the grip of this distant enigma, reminding us that even the lack of something can be as telling as its presence. And somewhere in that void, Eris keeps its secrets, waiting for the day we come close enough to listen. When astronomers point their spectroscopes at Eris, The light bouncing back tells a story that doesn't match any other world we've studied. The spectral signatures, unique fingerprints of light absorption and reflection, reveal a surface coated in substances that defy easy explanation. While most Kuiper Belt objects show simple spectra dominated by methane or water ice, Eris's light patterns contain jagged, unexpected dips and spikes, as if its frozen plains are sprinkled with materials we've barely encountered in the solar system. The most prominent anomaly comes from the near-infrared range, where Eris's spectrum shows a pronounced kink that shouldn't exist on a world this cold. On Earth, similar patterns are associated with complex organic molecules like tholins, the same compounds that give Titan its orange haze and Pluto its reddish stains. But here's the twist: tholins usually darken surfaces over time, yet Eris remains dazzlingly bright. This suggests its organics might be arranged in a highly reflective crystalline structure, or perhaps mixed with something even more exotic. Some researchers point to signatures resembling acetylene or hydrogen cyanide ices, compounds so volatile they rarely survive long in space. Finding them on Eris would be like discovering a freezer preserving delicate chemicals from the dawn of the solar system. Then there's the methane mystery. While Eris's spectrum confirms the presence of methane ice, the wavelengths at which it absorbs light don't quite match the pure methane found on Pluto or Neptune's moon Triton. The deviations hint that Eris's methane might be trapped in a different crystalline form, possibly mixed with nitrogen or ethane in a lattice that changes how it interacts with light. Picture ice not as a simple solid, but as an intricate molecular cage, subtly altering its properties based on what's trapped inside. The wildest theories propose even stranger possibilities. A few controversial studies suggest fleeting spectral lines that could indicate crystalline carbon dioxide or clathrate hydrates, ice-like compounds that imprison gas molecules in their structure. On Earth, clathrates exist in ocean depths and permafrost, storing vast amounts of methane. On Eris, they might explain how volatile gases persist near the surface despite the cold. Even more speculative is the idea of radiation-modified ices, where cosmic rays have transformed simple molecules into complex polymers, creating a surface layer unlike anything in our current databases. Of course, spectral data from such a distant world comes with caveats. Earth-based telescopes must peer through our own atmosphere, which introduces noise, while the faintness of Eris's signal leaves room for interpretation. Some scientists argue these exotic signatures could be artifacts trick of the light caused by observational limits rather than genuine chemistry, but that skepticism only fuels the debate. If the anomalies are real, they paint Eris as a cosmic alchemist brewing compounds we've never seen in the wild. If they're illusions, they reveal just how little we understand about interpreting light from the solar system's edge. Perhaps the most tantalizing clue lies in what the spectra don't show. Despite Eris's density suggesting a rocky core, there's no clear evidence of silicates or metals in its reflected light. This absence implies its surface might be thoroughly insulated by miles of exotic ice, hiding its deeper secrets from prying telescopes. It's a reminder that Eris isn't just challenging our expectations, it's rewriting the playbook on how dwarf planets evolve and what treasures might lurk in the frozen dark beyond Neptune. Most dwarf planets pirouette through space with the grace of spinning tops, completing rotations in just a few hours. But Eris, it moves like a cosmic tortoise, turning just once every 25 hours and 54 minutes. That's slower than Earth's 24-hour day from a world barely a fraction of our planet's size. This sluggish spin defies expectations, especially when compared to Pluto's snappy 6-day rotation or Haumea's dizzying 4-hour whirl. So what's putting the brakes on Eris? The prime suspect is Dysnomia, Eris's enigmatic moon. Tidal forces between celestial bodies can act like invisible hands, slowing rotations over time, just as Earth's gravity gradually lengthens the moon's day. Dysnomia's peculiar orbit, tilted and stretched, might be tugging on Eris asymmetrically, sapping its spin energy like a lopsided brake pad. But here's the catch. Calculations suggest Dysnomia is too small and distant to account for all of Eris's slowdown. Even after billions of years, their gravitational dance shouldn't have slowed Eris this dramatically, unless, of course, Dysnomia wasn't always this modest. Some models propose the Moon once orbited much closer, exerting stronger tidal forces before migrating outward. Then there's the collision theory. If Eris suffered a colossal impact early in its history, perhaps the same cataclysm that birthed Dysnomia, the sheer violence of that event could have nearly halted its rotation. Picture a cosmic billiard ball struck dead center by another massive object, leaving it wobbling like a top running out of steam. The problem: most giant collisions tend to speed up rotations by transferring angular momentum, not sap them. For Eris to end up this slow, the impact would have needed impossibly precise geometry, like a head-on strike from an object moving retrograde, essentially cancelling out Eris's spin like a hand grabbing a merry-go-round. The plot thickens when we consider Eris's density. Its unusually high mass for its size suggests a composition packed with heavy elements, which could influence rotational physics in ways we don't fully understand. Dense materials might redistribute internally over time, shifting the world's balance like a figure skater pulling their arms in except in reverse, gradually slowing the spin as mass concentrates toward the core. Perhaps the most radical idea is that Eris never spun quickly to begin with. While most solar system objects inherited rapid rotations from the swirling chaos of the protoplanetary disk, Eris might have formed through gentler mergers of smaller bodies, never building up significant angular momentum. Or its orbit's extreme tilt hints at a history of gravitational perturbations from Neptune or unseen bodies events that could have systematically drained its rotation like cosmic theft. What makes this enigma so compelling is that every explanation leaves loose ends. If tides slowed Eris, why hasn't the same process affected similar worlds? If a collision did it, where's the debris? And if Eris is just built differently, what does that say about the violent and varied histories of dwarf planets? Until we can study this slow-motion world up close, its leisurely spin remains one of the Kuiper Belt's most puzzling riddles, a celestial lullaby out of sync with the solar system's rhythm. Eris didn't just shake up our solar system, it tore through astronomical traditions with a name that couldn't have been more fitting. When this distant world was discovered in 2005, the team behind its detection faced a dilemma. What do you call a celestial body that had just thrown planetary science into chaos? Their choice, Eris, after the Greek goddess of strife and discord, was a cheeky nod to the firestorm it ignited, because this wasn't just another Kuiper Belt object. Its existence forced scientists to confront a question they'd avoided for decades. What exactly is a planet? The controversy began when measurements suggested Eris might be larger than Pluto. Suddenly, the solar system's cozy 9-planet club faced an existential crisis. If Pluto remained a planet, wouldn't Eris have to join it? And what about the other icy worlds lurking in the Kuiper Belt? The International Astronomical Union found itself in a bind, culminating in their infamous 2006 vote that introduced the term dwarf planet, a decision that demoted Pluto and left Eris as both a scientific milestone and a cultural flashpoint. Critics argued the new definition was arbitrary, while supporters saw it as long overdue clarity. Meanwhile, Eris's name became a rallying cry for those who felt the process had been rushed, a cosmic symbol of bureaucratic discord. But here's where it gets ironic. Eris almost didn't get its provocative name at all. Early suggestions leaned toward more neutral mythological figures like Lila, a Hindu goddess of play. The Discovery team's leader, Mike Brown, later admitted he chose Eris partly for the controversy, a wink to how its discovery had ruined everything for Pluto enthusiasts. The IAU initially resisted, fearing it sounded too combative, but eventually relented. In doing so, they unknowingly cemented Eris's legacy as more than just a frozen world. It became a metaphor for scientific upheaval, a reminder that even in the rigid world of astronomy, progress often comes with growing pains. The naming debate reveals something deeper about how we categorize the cosmos. Before Eris, the line between planets and smaller bodies seemed clear. Afterward, we had to grapple with messy realities that nature doesn't always fit into neat boxes, and that definitions evolve as our understanding grows. Eris didn't just disrupt the solar system's map, it challenged us to rethink how we impose order on the universe's chaos. And that, perhaps, is the most fitting tribute to its namesake goddess, a celestial agent of change, spinning silently in the dark, forever altering how we see our place in the stars. Eris's surface remains one of the solar system's most tantalizing blind spots, a world we've studied from afar but never seen up close. Unlike Pluto, where New Horizons sent back crisp images of nitrogen glaciers and mountain ranges, Eris exists in our telescopes as little more than a brilliant speck. The best images we have, captured by Hubble and ground-based observatories, show a pixelated blob no more detailed than a snowball glimpsed through frosted glass. Yet even these crude glimpses reveal hints of an alien landscape hiding beneath that shimmering facade. What little we can discern comes from clever tricks of astronomy. By watching how Eris reflects light at different angles, a technique called photometry, scientists have detected subtle variations in brightness that suggest surface features. Some areas appear slightly darker or more textured than others, possibly indicating impact craters, sprawling plains, or jagged mountain ranges. The most intriguing data comes from stellar occultations, where Eris passes in front of distant stars. These events cast fleeting shadows that reveal profile details, like an X-ray of its silhouette. One such observation in 2016 hinted at an unexpectedly smooth edge, as if parts of Eris lacked the deep craters common on similarly sized worlds. This smoothness raises wild possibilities. Perhaps Eris has active geology refreshing its surface, like icy volcanoes spewing fresh slush to fill in ancient scars. Or maybe its mirror, like methane frost flows like an ocean of glass, slowly burying terrain under glowing sheets of ice. There's even a chance its surface behaves unlike anything we've seen, a brittle shell fracturing under pressure from below, creating fractal patterns invisible to our current tools. The biggest mystery, bright spots. Just as Pluto's heart-shaped tombow Regio stunned astronomers, Eris may have its own stark contrasts. Infrared scans suggest localized regions reflect even more light than the already glaring plains, as if patches of ultra-pure ice or exotic materials dot the landscape. Some scientists speculate these could be cryovolcanic vents, where fresh frost erupts onto the surface. Others propose cold geysers, slow-motion plumes of nitrogen gas freezing instantly in the void, creating glittering deposits. Future missions could rewrite everything we think we know. Imagine a probe swooping past Eris, revealing canyons deeper than the Grand Canyon, or ice spires towering over Martian cliffs. The dwarf planet's density suggests its rocky core might bulge close to the surface in places, creating jagged peaks of primordial stone poking through the ice. There could be vast, craterless plains, evidence of recent resurfacing, or webs of cracks hinting at underground oceans. And what if those bright spots aren't geological at all? Far-fetched as it sounds, some theorists float the idea of crystalline structures formed by exotic chemistry, a frozen equivalent of mineral veins on Earth. Until we send a spacecraft, Eris's true face will stay hidden. But that uncertainty is what makes it thrilling. Every unexplored world in history has shattered expectations when finally seen up close. Mountains where we predicted flatlands, volcanoes where we imagine deserts, Eris, with all its contradictions, promises to deliver that same cosmic surprise, a reminder that the solar system's most fascinating stories often lurk in the pixels we can't quite bring into focus. Eris isn't just unusually dense for a dwarf planet, it's rewriting the book on what small, icy worlds can hide beneath their surfaces. Tipping the scales at nearly 2.5 grams per cubic centimeter, it outdensities Pluto by a staggering margin, packing more mass into a slightly smaller volume. To put that in perspective, if you could hold Eris and Pluto in your hands like snowballs, Eris would feel noticeably heavier, as if someone had slipped lead weights into its core. This density isn't just an academic curiosity, it's a roadmap to understanding what's happening beneath that shimmering icy shell. The leading theory points to a massive rocky core, possibly making up 70% or more of Eris's total mass. That's far more than the 50% rock-to-ice ratio seen in most Kuiper Belt objects, suggesting Eris formed under unusual circumstances. One possibility is that it originated closer to the Sun, where stronger radiation blew away lighter ices during its formation, leaving behind a higher concentration of dense silicates and metals. Later, gravitational interactions with Neptune could have flung it outward, leaving it stranded in the Kuiper Belt with its peculiar composition intact. Imagine a cosmic mining operation gone wrong, scattering precious ore into the void. But here's where the mystery deepens. If Eris does have such a large rocky core, why hasn't its internal heat melted the surrounding ice? On other worlds, like Jupiter's moon Europa, radioactive decay in rocky cores maintains vast subsurface oceans. Yet Eris shows no definitive signs of liquid layers, just that baffling mix of high density and surface brightness. Some researchers speculate its core might be oddly cold, packed with dense but non-radioactive minerals like iron or nickel that generate little internal warmth. Others propose an even stranger idea, that Eris's core isn't uniform at all, but a fragmented mix of rock and metal suspended in the ice like chocolate chips in cookie dough. This could explain the density without requiring a single massive heat source. Then there's the wild card, exotic ices. At the crushing pressures found deep inside Eris, water ice can morph into bizarre high-density phases like Ice 6 or Ice 7, crystalline structures that behave more like rock than snow. These exotic ices could be masquerading as rock in our density calculations, creating the illusion of a larger core than actually exists. It's like trying to guess what's inside a locked safe by its weight, not realizing the walls themselves might be made of lead. Perhaps the most tantalizing clue comes from Eris's moon Dysnomia. The way these two bodies tug on each other suggests Eris's mass isn't perfectly distributed. There might be dense pockets offset from the center, like a lopsided engine in a car. This irregularity could hint at a violent past where colossal impacts scrambled Eris's interior, leaving behind dense fragments scattered beneath the ice. Or it might point to ongoing geological processes, with heavy elements slowly sinking toward the core in a glacial version of plate tectonics. Every explanation raises new questions. If Eris has such a large core, why doesn't it show more evidence of past volcanic activity? If it's packed with exotic ices, why does its surface appear so pristine? And if its density comes from collisions, where are the other similarly dense Kuiper Belt objects? Each hypothesis forces us to reconsider not just Eris, but how all dwarf planets form and evolve. One thing's certain, beneath that glittering shell lies something extraordinary, a hidden chapter in the solar system's history waiting to be read. Methane on Eris shouldn't exist, at least not in the quantities we're seeing. This simple hydrocarbon, common in planetary atmospheres and icy surfaces, has a fatal flaw in the Kuiper Belt: sunlight. Over billions of years, the relentless barrage of solar radiation should have broken Eris's methane down into heavier, darker compounds called tholins, leaving its surface stained a dull reddish-brown like Pluto's heart-shaped plains. Yet there it is, gleaming bright, as if freshly laid. It's the cosmic equivalent of finding unwrapped candy in the rain that somehow never got wet. The answer might lie in what's happening beneath the ice. On worlds like Neptune's moon Triton, geysers spew nitrogen gas into the void, creating ephemeral atmospheres and refreshing the surface. Eris could be experiencing something similar, with hidden reservoirs of methane occasionally erupting through cracks in its frozen crust. These outbursts wouldn't be the violent plumes we see on Enceladus, more like slow, oozing leaks where methane gas seeps up from below and freezes instantly in the vacuum. Picture a frozen soda can cracking open in the freezer, its contents crystallizing the moment they hit the air, but methane's persistence raises even wilder possibilities. Some scientists speculate Eris might harbor a cold storage mechanism, unique geological processes that recycle methane rather than losing it to space. On Earth, permafrost traps ancient methane in icy cages called clathrates. Eris's extreme cold and high pressure could create similar structures near its surface, locking methane away until slight temperature shifts release it in measured bursts. Alternatively, seasonal changes might play a role. As Eris inches closer to the Sun during its 257-year orbit, fleeting warmth could vaporize trace amounts of subsurface methane, which then refreezes as frost when temperatures plummet again. The most tantalizing clue comes from spectral data. The methane detected on Eris isn't quite the same as the pure form found on Pluto. Its light signature suggests the molecules might be trapped in nitrogen ice crystals or mixed with other volatiles, altering how they react to sunlight. This dirty ice could act like a protective coating, slowing the breakdown process dramatically. Imagine methane molecules encased in transparent armor, shielding them from the ravages of solar radiation while still reflecting light with dazzling efficiency. Of course, there's always the chance we're missing something fundamental. Recent lab experiments show that methane irradiated at temperatures near absolute zero can form unusual crystalline structures that resist chemical change far longer than expected. If Eris's surface chemistry favors these exotic configurations, it might explain the paradox without requiring constant replenishment. Or perhaps the methane isn't primordial at all, but the product of ongoing chemical reactions deep within the ice, where residual heat or radioactive decay transforms simpler compounds into fresh methane over geologic time. The implications stretch far beyond one distant world. If Eris is actively recycling methane, it challenges our assumptions about how volatile substances behave in the outer solar system. Other Kuiper Belt objects might harbor similar hidden reservoirs, transforming these frozen relics into dynamic worlds with complex chemical cycles. And if that's true, it raises an even more profound question. What else is hiding beneath that glittering surface, waiting to rewrite the rules of planetary science? Eris gleams like a celestial pearl against the cosmic dark, its surface so pale it borders on pure white, a stark contrast to the rusty hues of its Kuiper Belt neighbors. This unexpected whiteness isn't just a cosmetic quirk, it's a scientific puzzle that challenges our understanding of how cosmic chemistry works at the solar system's edge. Most distant icy objects like Pluto or Makemake wear a reddish coat tinted by eons of solar radiation cooking their surface ices into complex organic gunk. Yet Eris defies the trend, reflecting sunlight with the brilliance of a freshly bleached seashell. The secret might lie in what's missing from Eris's surface. On other Kuiper Belt objects, methane and nitrogen ices slowly transform into dark, ruddy tholins when bombarded by ultraviolet light, a process akin to sunscreen turning brown after years in the sun. But Eris's spectrum shows barely a trace of these reddish contaminants. One possibility is that its orbit keeps it just cold enough to preserve its ices in a pristine state. While Pluto's elliptical path occasionally brings it close enough to the Sun for seasonal tholin production, Eris's more distant trajectory might lock its surface in a perpetual deep freeze, slowing chemical weathering to a crawl. Imagine two paintings left outside, one under a scorching sun, the other in shade. Eris is the protected masterpiece, its colors unfaded by time. Yet temperature alone doesn't explain everything. Some similarly frigid Kuiper Belt objects still manage to redden over time, which suggests Eris has an active defense mechanism. Its high reflectivity hints at constant resurfacing, with fresh ice welling up to bury older, darker material before radiation can stain it. Picture a self-cleaning oven continually shedding its baked-on grime. This process could be driven by subtle geological activity, perhaps sluggish nitrogen glaciers creeping across the surface, or the occasional belch of methane gas from below, leaving behind a glittering frost. The plot thickens when we consider Eris's composition. Recent studies suggest its methane might not be free floating on the surface but trapped in a crystalline lattice with nitrogen, forming a hybrid ice that resists radiation damage better than pure methane. Laboratory experiments show these mixed ices can remain startlingly white even under simulated space conditions, like a snowbank packed so tightly it repels dirt. There's even speculation that Eris's surface ices rearrange themselves at the molecular level when hit by cosmic rays, healing microscopic blemishes before they can accumulate into visible stains. But the most radical theory skips chemistry altogether. A handful of researchers propose that Eris's color comes from its extreme distance from the sun, so far that cosmic rays, not sunlight, dominate its weathering. These high-energy particles flung from distant supernova might bleach Eris's surface instead of darkening it, like ultraviolet light fading a poster left in a window. If true, it would mean Eris isn't just preserving primordial ice. It's actively being whitened by the galaxy itself, a celestial canvas repainted by interstellar forces. The implications stretch beyond one oddball world. If Eris's pallor stems from unique chemistry, it suggests the outer solar system hosts a diversity of surface processes we've barely begun to catalog. If it's due to cosmic rays, it could redefine how we interpret the colors of all distant objects. Either way, this icy enigma proves that even something as simple as color can hide profound cosmic secrets, and that sometimes the most striking mysteries are the ones staring us right in the face. Most worlds in the solar system wear a cloak of dust, the fine, gritty remnants of countless cosmic collisions clinging to their surfaces and surroundings. Yet when astronomers peer at Eris, they find something peculiar, an almost eerie lack of particulate matter floating nearby. No dusty halo, no debris rings. Just empty space stretching around this icy world like a freshly swept floor. This absence is puzzling, especially when compared to Pluto, where New Horizons spotted layers of haze drifting above glacial plains. So where did all the dust go? One possible explanation lies in Eris's extreme orbit. Unlike Pluto, which cruises through the relatively crowded inner Kuiper Belt, Eris spends most of its elongated journey in a sparse no-man's land beyond Neptune's gravitational influence. Fewer neighboring objects mean fewer collisions, and fewer collisions mean less pulverized rock and ice to create dust in the first place. Think of it like driving on a deserted highway versus a congested city street. The chances of kicking up debris drop dramatically when there's hardly any traffic. But there's another twist to Eris's slow rotation. Most small bodies spin fast enough to fling loose particles outward, creating temporary dusty envelopes. Eris's leisurely day, nearly 26 hours long, barely generates enough centrifugal force to dislodge surface grains. Any dust that does lift off likely falls back quickly, like flour settling in a jar that's only gently shaken. This could explain why even microscopic particles seem absent from its immediate vicinity. Then there's the question of what happens to the dust that should be there. Over billions of years, even a few impacts should have littered Eris's neighborhood with some debris. The solar wind, a constant stream of charged particles from the sun, usually pushes this dust away over time, but at Eris's distance, the wind is so weak it's practically a breeze. That's where Dysnomia might play a role. Eris's moon, though small, orbits just close enough to potentially act like a cosmic vacuum cleaner, its gravity capturing stray particles that would otherwise hang around. Picture a child running through a cloud of dandelion seeds, gathering them in their wake. The most provocative theory involves Eris's surface chemistry. Its methane-rich ice might behave like a gigantic electrostatic sheet, repelling dust particles instead of attracting them. In lab experiments, certain ices build up strong electric charges when exposed to sunlight, effectively pushing away nearby matter. If Eris's frozen plains crackle with this invisible force field, even the finest grains could be banished to space, leaving its surroundings immaculate. Of course, there's always the chance we're not seeing the full picture. Dust around distant objects is notoriously hard to detect from Earth, and Eris's blinding reflectivity might simply be washing out faint traces of particulate matter in telescope images. Future missions could reveal wispy rings or faint hazes too subtle for current instruments, or confirm that this dwarf planet truly exists in a pristine bubble, untouched by the chaotic scattering that marks nearly every other world we've studied. Whatever the answer, Eris's dust-free zone adds another layer to its mystique. Is it the product of orbital isolation, unique geology, or something even stranger? In a universe where cosmic clutter is the norm, cleanliness might just be this world's most baffling trait. Weather on Eris sounds like an oxymoron. How could a world with barely any atmosphere experience storms or seasons? Yet this distant dwarf planet might hide meteorological secrets far stranger than anything on Earth. Without thick atmospheric layers to drive traditional weather systems, Eris's version of climatic activity would play out in ultra-slow motion, governed by the faintest whispers of heat and the peculiar properties of its exotic ices. Imagine a landscape where snowfall happens in reverse. During Eris's rare close approaches to the Sun still farther out than Pluto's orbit, pockets of nitrogen or methane ice might briefly warm enough to sublimate directly from solid to gas. These vapors wouldn't form clouds. Instead, they'd slither along the surface like phantom rivers, following temperature gradients until they refreeze in colder regions. The result, glacial flows thinner than tissue paper, creeping across the plains at maybe an inch per century. Some researchers speculate these processes could create frost tides, seasonal shifts where entire hemispheres brighten or darken as ices migrate with the subtle temperature changes of Eris's 257-year orbit. Then there's the possibility of electrostatic weather. On airless worlds like Earth's moon, solar radiation can electrically charge dust particles, making them levitate in temporary dust storms. Eris's surface, laden with methane and possibly nitrogen frost, might experience something similar, but with ice crystals instead of dust. Picture microscopic diamonds of frozen methane lifting off the ground in invisible fountains, caught in weak electrostatic currents before settling back hours or days later. These diamond mist events wouldn't resemble terrestrial storms, but they could still count as weather, just of a kind we've never witnessed firsthand. The wildest theories involve cryovolcanic fog. If Eris has even trace internal heat, gases seeping from underground could momentarily form localized hazes before freezing out. On Neptune's moon Triton, similar processes create ephemeral nitrogen geysers visible from space. For Eris, these outbursts would be far more subdued, perhaps just a faint shimmer hovering over fissures for a few hours before vanishing into the void. Some astronomers suggest these microatmospheres might leave detectable chemical fingerprints, like methane snowflakes with slightly different isotopic ratios from the surrounding ice. Of course, all this assumes Eris is geologically dead, which its density and reflectivity suggest it isn't. If active cryovolcanism or tidal heating from Dysnomia keeps parts of its interior warm, we could be looking at weather systems powered by underground forces rather than sunlight. Imagine steam vents erupting not with water vapor, but with neon-colored nitrogen plumes that instantly crystallize into falling glitter, or pressurized methane pockets bursting through the ice like champagne corks, creating temporary pressure differentials that stir the scant surrounding gases into brief, violent whirlwinds. The real challenge in studying Eris's weather is time, with seasons lasting decades and storms potentially unfolding over centuries. Human observations capture mere snapshots of processes too slow to comprehend. Telescopes might catch the aftermath of a storm, say, a fresh bright patch suggesting recent frost deposition without witnessing the event itself. It's like trying to study Earth's climate by looking at a single frame from a century-old film reel. Yet these phantom weather patterns matter. If ices truly migrate across Eris's surface, they could transport heat, alter reflectivity, and even bury or expose geological features over epochs. Weather, even in this alien form, might be the sculptor behind the world's baffling brightness, the architect of its mysteriously smooth plains. And that makes Eris's unseen atmospheric ballet more than just a curiosity. It's a key to understanding how the solar system's most distant worlds stay dynamic against all odds. Most dwarf planets we've studied hum with faint magnetic fields, cosmic fingerprints of churning metallic cores or subsurface oceans, but Eris stands apart in its eerie silence. Despite advanced searches using Earth's most sensitive instruments, no detectable magnetic signature radiates from this distant world. The absence raises a fundamental question: is Eris geologically dead, or are we missing something hidden beneath its icy shell? The simplest explanation points to a frozen core. Magnetic fields typically require two ingredients: conductive fluid in motion and rotation. Earth's field springs from its molten iron outer core, while dwarf planets like Ceres may generate weak fields through salty subsurface oceans. Eris's sluggish spin, once every 26 hours, provides minimal rotational energy to power a dynamo. Combine that with its extreme distance from the Sun, and the recipe for geological activity seems bleak. Without internal heat to keep metals molten or brines liquid, Eris's core could be locked in permanent permafrost, its primordial magnetic field long since faded into silence. Yet contradictions emerge when we examine Eris's density. Its unusually high mass suggests a substantial rocky core, rich in iron and nickel metals that should, in theory, retain enough radioactive decay to generate at least some residual warmth. Even Pluto, smaller and less dense, shows hints of a subsurface ocean that might induce minor magnetic fluctuations. If Eris's core truly is colder than expected, it challenges our models of how dwarf planets retain heat over billions of years. Perhaps its composition includes unexpected insulating layers, like a thick mantle of exotic ices trapping core heat like a thermos bottle. Then there's the measurement problem. Detecting magnetic fields at Eris's distance is like trying to hear a whisper across a football stadium. Earth-based telescopes lack the precision to identify weak fields, and no spacecraft has ventured close enough for direct readings. Even Pluto's magnetic environment remains debated. New Horizons lacked a dedicated magnetometer, forcing scientists to infer its properties indirectly through atmospheric interactions. Eris could harbor a feeble field that's simply drowned out by cosmic noise or fluctuating at frequencies our instruments can't catch. The most tantalizing possibility involves intermittent activity. Some moons, like Saturn's Enceladus, generate sporadic magnetic pulses tied to geyser eruptions rather than steady dynamos. If Eris experiences similar bursts, say, from occasional cryovolcanic events or tidal flexing by Dysnomia, its magnetic field might flicker on and off like a failing light bulb, invisible to our snapshot observations. We'd need continuous monitoring over years to catch these ephemeral signals, a task currently beyond our technological reach. Or perhaps Eris represents a new class of celestial object, one where magnetic fields form through unconventional means. Laboratory experiments show that certain high-pressure ices, like those suspected in Eris's mantle, can conduct electricity when laced with ammonia or salts. Under the right conditions, these ionic oceans might generate weak currents without liquid water or molten metal, creating magnetic effects too subtle for current detection. It's a reminder that the universe often defies our tidy classifications, inventing rules we've yet to imagine. Until a probe makes the long journey to Eris, its magnetic silence will remain open to interpretation. Is it a frozen fossil, its dynamo stilled by time, a world hiding active layers beneath an icy shield, or something entirely novel, rewriting the physics of how small planets function? The absence of answers only deepens the allure, proving that sometimes what we don't detect can be as revealing as what we do. Eris's frozen plains hide a tantalizing possibility: cryovolcanoes, the ice-covered cousins of Earth's fiery mountains. While we've spotted these frosty fountains erupting on Pluto, Enceladus, and Europa, Eris remains a blank slate, its surface too distant for close-up scrutiny. Yet the clues we can detect suggest this dwarf planet might harbor its own version of cold volcanism, sculpting its landscape in ways we've yet to imagine. Take Pluto's cryovolcanoes, for example. When New Horizons glimpsed Right Mons, a towering structure suspected of spewing slushy nitrogen or water-ammonia mixes, it proved even distant worlds can stay geologically alive. These features thrive on residual heat, radioactive decay, or gravitational squeezing that keeps subsurface liquids just warm enough to burst through icy crusts. Eris shares key traits with Pluto, a likely rocky core, reflective ices, and density anomalies hinting at internal complexity. But here's the twist: Eris's greater mass means its core could retain heat longer, potentially fueling cryovolcanic activity even now. Picture a pressure cooker buried under miles of ice, occasionally venting its steam into the void. Then there's Europa, Jupiter's ocean moon, where cryovolcanism springs from tidal flexing rather than radioactive warmth. Eris lacks a giant planet's gravitational pull, but its moon Dysnomia might play a similar role on a smaller scale. Their tight orbital dance could generate subtle friction, flexing Eris's interior like a cosmic stress ball. While the effect would be weaker than Europa's over billions of years, even faint tidal heating might soften deep ice enough to create pockets of slush or liquid. If those pockets found a path to the surface through cracks or weak spots in the crust, we could be looking at cryovolcanoes oozing methane-laced slurries instead of water. So why haven't we found definitive proof? The challenge lies in Eris's glare. Its blinding reflectivity masks surface details, making it nearly impossible to spot the domes or flows that betray cryovolcanism elsewhere. On Pluto, dark streaks and craterless plains flag recent resurfacing, but Eris's uniform brightness offers no such breadcrumbs. Even its thermal signatures, which might reveal warm fractures or vents, are too subtle for current telescopes to pass from Earth. The strongest hints come from Eris's methane. Unlike Pluto's patchy, tholin-stained deposits, Eris's frost appears unnaturally fresh, as if regularly replenished. Cryovolcanic vents could explain this, exhaling methane vapor that freezes into new layers of pristine ice. Imagine a world where geysers erupt not in fiery plumes, but in slow-motion curtains of glittering frost, their remnants spread by weak winds or electrostatic levitation. Yet skeptics argue Eris's cold heart leaves little room for such drama. Without Pluto's seasonal thaws or Europa's tidal furnace, any internal heat might be locked away too deep to reach the surface. Its high density could stem from a compact, inactive core, with thick, insulating ice preventing warmth from escaping. And while Dysnomia's gravity might stir Eris slightly, calculations suggest the effect would be trivial, like trying to warm a glacier with a candle. The debate won't settle until we glimpse Eris up close. Future missions might find cryovolcanic peaks dwarfing Everest, their slopes gleaming with exotic snows. Or they could reveal a fossilized world, its potential for eruptions long frozen in time. Either way, Eris reminds us that the solar system's farthest reaches hold surprises where even ice, pushed to its limits, can defy expectations. Eris's origin story reads like a cosmic detective novel, with contradictory clues pointing to multiple possible pasts. Did this misfit dwarf planet form peacefully in the Kuiper Belt, or was it violently ejected from the solar system's inner realms? The evidence paints a picture that's anything but clear-cut. On one hand, its composition, rich in methane and nitrogen ices, matches other Kuiper Belt natives like Pluto. Yet its extreme orbit and puzzling density suggest a history far more turbulent than most of its icy neighbors. The classic formation theory places Eris's birth squarely in the Kuiper Belt, condensing from the primordial disk of dust and gas that swirled around our young sun. In this scenario, it would have grown slowly over millions of years, gently accumulating ices and rock until reaching its present size. This would explain its similarities to other trans-Neptunian objects like Makemake or Haumea. But the plot thickens when we examine its orbit. That wild 44-degree tilt and stretched elliptical path don't fit the orderly pattern of most Kuiper Belt residents. It's like finding a penguin in a desert. Something clearly doesn't belong. That anomaly fuels the rival exile theory, which proposes Eris began life much closer to the Sun, perhaps near Neptune or even Uranus. In this dramatic version of events, gravitational interactions with the ice giants, particularly Neptune, could have slung the young Eris outward in a cosmic game of pinball. Computer simulations show such encounters can fling objects into bizarre, tilted orbits resembling Eris's path. The dwarf planet's surprising density supports this idea, as formation closer to the Sun would expose it to stronger radiation, boiling away lighter ices and leaving behind a higher concentration of heavy rock and metal. Yet both theories hit major snags. If Eris formed locally in the Kuiper Belt, why doesn't it share the more circular, flat orbits of its supposed siblings? And if Neptune ejected it, why does its chemical makeup so closely match classic Kuiper Belt objects rather than inner solar system refugees? Some researchers propose a middle ground, that Eris originated in the Kuiper Belt but suffered a catastrophic collision early in its history, altering both its orbit and internal structure. The impact could have stripped away surface layers, exposing denser underlying material while imparting the gravitational kick needed to tilt its path. This would explain both its orbital oddities and unusual density without requiring a dramatic migration. The most radical hypothesis suggests Eris might not be from our solar system at all. A few astronomers point to its orbital peculiarities as potential evidence it was captured from interstellar space, a frozen wanderer adopted by our sun's gravity. While intriguing, this idea struggles to explain why Eris's composition aligns so neatly with other Kuiper Belt objects, unless, of course, interstellar space harbors more similar icy worlds than we've assumed, a possibility that itself would rewrite astrophysics textbooks. Gaps in our knowledge glare like uncharted continents on an ancient map. We lack crucial data about Eris's internal structure that could confirm or contradict these origin stories. Without knowing the precise ratios of isotopes in its ice's chemical fingerprints that vary between different solar system regions, we're left guessing at its birthplace. Even the timing of its possible ejection remains fuzzy. Did it happen during the solar system's chaotic youth, or could gravitational tugs have reshaped its orbit more recently? Perhaps the most humbling realization is that Eris might not fit neatly into any single category. Like many celestial bodies, its history could be a patchwork of multiple events: local formation followed by disruptive encounters, or partial ejection with lingering chemical ties to its birthplace. Every new discovery about this distant world seems to add complexity rather than clarity, proving that the edges of our solar system still hold mysteries capable of upending even our most carefully constructed theories. And until we can study samples from its surface or send a probe to scrutinize its features up close, Eris's true origin story will remain as elusive as the distant sunlight glinting off its frozen plains. Most moon systems in the solar system follow a simple hierarchy, a dominant planet with tiny satellites orbiting like attendants. But Eris and Dysnomia break the mold, behaving less like a parent and child and more like cosmic siblings locked in an intricate dance. With Dysnomia estimated to be roughly 1/10 Eris's size, their mass ratio is startlingly close compared to other dwarf planet-moon pairs. Pluto's largest moon, Charon, for instance, is only 1/8 its mass, already considered unusually large. This near balance transforms Eris and Dysnomia into something far stranger, a borderline binary system where both bodies orbit a common point in space, constantly tugging each other in a delicate gravitational seesaw. What makes this pairing so peculiar isn't just the size, it's the physics-defying odds. Conventional moon formation favors two scenarios. Either a collision ejects debris that coalesces into a much smaller satellite like Earth's moon, or a planet captures a passing object like Mars's irregularly shaped moons. Neither neatly fits Eris's situation. For a collision to spawn Dysnomia at its current size, the impact would need near-perfect symmetry, a glancing blow so precise it sheared off just enough material without disrupting Eris entirely. Statistically, such an event borders on miraculous, yet capture seems equally implausible. Dysnomia's composition and reflectivity match Eris too closely for it to be a random Kuiper Belt interloper. It's like finding two snowflakes with identical patterns in different blizzards. The binary dynamic introduces its own riddles. In most systems with such closely matched masses, tidal forces would quickly circularize their orbits. Yet Dysnomia follows an elongated, tilted path around Eris, as if frozen mid-adjustment. Some models suggest this could be a snapshot of an evolving system, Dysnomia slowly spiraling outward over billions of years, its orbit not yet smoothed by gravity. Others propose that Eris's unusually slow rotation stalled the process, leaving their dance forever off balance. Perhaps the most tantalizing clue lies in their reflectivity. Both bodies shine with nearly identical brightness, a trait unheard of in other binary pairs. This could hint at shared resurfacing mechanisms. Maybe cryovolcanic activity on Eris regularly coats both worlds in fresh frost, or gravitational flexing generates heat that keeps their surfaces oddly pristine. Every explanation raises new questions. If they formed together, why hasn't Dysnomia migrated into a neater orbit? If captured, how did their compositions synchronize so perfectly? The answers might rewrite how we understand moon formation entirely, suggesting that at the solar system's edge, the rules bend in ways we're only beginning to glimpse. Eris's surface behaves like a cosmic laboratory, bombarded by high-energy particles from deep space, yet the way it reacts to these impacts defies all expectations. Cosmic rays, those atomic bullets hurtling through the galaxy at nearly light speed, typically leave clear marks on airless worlds, darkened patches where they've shattered surface molecules, creating telltale organic compounds. But Eris gleams untouched, its icy facade remaining stubbornly bright despite eons of particle bombardment. This anomaly suggests something extraordinary is either shielding its surface or erasing the damage as quickly as it forms. One explanation could lie in Eris's bizarre reflectivity. Most objects in the Kuiper Belt slowly redden under cosmic ray exposure, their ices transforming into dark tholins, a process we've observed on Pluto, Makemake, and even Saturn's moon. But Eris's mirror-like surface might be acting like a radiation shield. Laboratory experiments show that highly reflective methane ice can scatter incoming cosmic rays more effectively than darker materials, reducing their penetration depth. Picture sunlight glancing off a polished chrome sphere versus sinking into a charcoal brick. If Eris's frost is arranged in a specific crystalline structure, it could be deflecting a significant portion of these high-energy particles before they have a chance to cause chemical changes. Then there's the atmospheric void to consider. Without even a wisp of gas to absorb or deflect cosmic rays, Eris's surface should theoretically bear the full brunt of their impact. But paradoxically, this absence might create a self-cleaning mechanism. On worlds with atmospheres, cosmic rays often interact with airborne molecules first, generating secondary particles that rain down more diffusely. Eris's naked exposure means each primary cosmic ray strikes with concentrated force, potentially blasting away its own damage over time. Imagine a sandblaster hitting the same spot repeatedly, scouring the surface clean before stains can set in. The wildest theories involve Eris's chemistry. Cosmic rays typically leave behind dark residues by breaking apart simple molecules like methane and reassembling them into complex organics. But if Eris's ices contain trace amounts of ammonia or salts common in the outer solar system, these additives could trigger alternative reactions. Instead of forming dark tholins, radiation might produce volatile compounds that sublimate away into space, leaving no visible trace. It's the difference between spilling coffee on a table leaving a stain and spilling dry ice which vanishes without residue, or perhaps the answer lies underground. If Eris's surface ices are in constant motion, creeping glacier-like from seasonal changes or cryovolcanic renewal, fresh material could be continually emerging to cover any radiation scars. Pluto's heart-shaped Sputnik Planitia shows similar resurfacing, albeit driven by atmospheric cycles Eris lacks. But with Eris's high density suggesting possible internal heat, even subtle shifts in its icy shell might act like a conveyor belt, burying damaged layers before they can accumulate. The implications stretch beyond one icy world. If Eris truly resists cosmic ray weathering through some unknown mechanism, it could mean other Kuiper Belt objects have been hiding similar abilities. Telescopes might be underestimating their ages based on surface brightness, assuming darkening that never occurred. Or worse, we could be missing an entire class of radiation-defying materials that don't exist in our current models. Either way, Eris's defiance of cosmic rays isn't just a curiosity. It's a challenge to our understanding of how surfaces evolve in the most hostile environments of the solar system. And until we can sample that glittering terrain directly, the full story will remain just out of reach, as elusive as the particles themselves. The vast emptiness around Eris isn't just eerie, it's scientifically baffling. While Pluto plays host to at least 5 known moons and a suspected swarm of smaller bodies, Eris drifts through the Kuiper Belt in unsettling solitude, its only companion the enigmatic Dysnomia. Not a single comet, debris ring, or even a stray pebble has been definitively spotted in its vicinity. This stark contrast raises a fundamental question. In a region teeming with cosmic rubble, how does one of the largest objects end up so utterly alone? The gravitational dynamics tell part of the story. Eris's elongated orbit means it spends most of its time in the Kuiper Belt's sparsely populated outskirts, far from the denser zones where Pluto resides. Fewer neighbors mean fewer chances for gravitational encounters that might capture passing objects, but that's not the whole picture. Pluto's retinue of small moons likely formed from debris generated by ancient collisions, a process that should have occurred around Eris too, given its violent history. The fact that we see no such remnants suggests something has been clearing the area, like a cosmic janitor sweeping away the evidence. One possibility lies in Eris's slow rotation. Most dwarf planets spin quickly enough to fling loose material outward, creating temporary clouds of debris that eventually coalesce into moons or rings. Eris's sluggish day, stretching nearly 26 hours, lacks the centrifugal force to eject matter effectively. Any fragments created by impacts might simply fall back to the surface, like embers returning to a dying fire. Compare this to Haumea, another Kuiper Belt denizen, whose rapid spin fuels a surrounding debris ring and multiple moons. Eris's leisurely pace seems to trap its own wreckage rather than dispersing it. Then there's Dysnomia's role to consider. While small, this moon orbits just close enough to potentially destabilize any would-be satellites. Computer simulations show that objects venturing too near the Eris-Dysnomia gravitational duet would be ejected entirely or spiral inward to destruction within millennia, cosmic timescales too brief for us to witness the aftermath. It's a celestial balancing act where Dysnomia acts as both partner and bouncer, keeping their shared space ruthlessly tidy. But the most intriguing factor might be electrostatic. Eris's highly reflective surface suggests an unusual accumulation of electric charge, as frozen methane and nitrogen ices become ionized by distant sunlight. This could create invisible repulsive forces, pushing dust and small particles away like magnets with the same polarity. Laboratory experiments with similar ices show they can levitate micron-sized grains under space-like conditions, potentially explaining why no fine debris lingers nearby. Imagine trying to scatter iron filings around a powerful electromagnet. They'd simply refuse to settle. Of course, absence of evidence isn't evidence of absence. Our telescopes might simply lack the resolution to spot faint rings or tiny moons against Eris's blinding glare. Or perhaps any surrounding material is too dark or diffused to detect from Earth, like black sand scattered on a sunlit beach. Future missions could reveal delicate structures hidden in plain sight, wisps of ice crystals or swarms of boulders too sparse to cast noticeable shadows from afar. The deeper implication unsettles planetary scientists. If Eris truly exists in a self-imposed void, it challenges assumptions about how dwarf planets interact with their environments. Does its cleanliness hint at unseen forces reshaping the Kuiper Belt's architecture? Could other isolated objects share this peculiar trait, hiding in the darkness with equally pristine orbits? Until we venture closer, Eris's loneliness remains one of its most profound puzzles, a reminder that even in the crowded cosmos, some worlds choose to walk alone. Seasons on Earth mean shifting temperatures, changing leaves, and migrating storms, but on Eris, the concept warps into something far stranger. Without a substantial atmosphere to trap heat or drive weather systems, this distant world's seasonal shifts would play out in ultra-slow motion, governed by the faintest whispers of sunlight over its 257-year orbit. Yet the evidence suggests this isn't a static, unchanging freeze. Subtle variations in Eris's brightness hint at cycles unfolding across decades, as if the dwarf planet breathes in rhythms we're only beginning to decipher. Compare this to Pluto, where seasons paint dramatic strokes across the landscape. When New Horizons flew by in 2015, it captured Pluto's northern hemisphere thawing from its decades-long winter, nitrogen glaciers creeping across plains in sluggish rivers. These changes are possible because Pluto's thin but persistent atmosphere, mostly nitrogen with traces of methane and carbon monoxide, acts like a cosmic thermostat, redistributing ices as temperatures fluctuate. Eris, by contrast, has no such blanket. Any seasonal activity would need to work without atmospheric convection, relying instead on direct solar heating, or lack thereof, to drive its transformations. So how do seasons manifest on an airless world? The answer might lie in Eris's bizarre reflectivity. As it inches slightly closer to the Sun during its elliptical orbit, weak sunlight could penetrate translucent layers of methane and nitrogen ice, vaporizing trace gases just beneath the surface. These vapors wouldn't form clouds or winds. Instead, they'd migrate along temperature gradients, refreezing in colder regions like ghostly frost tides. Picture dry ice sublimating in a lab but on a planetary scale, a silent, slow-motion reshuffling of molecules across centuries. Infrared observations support this. Patches of Eris's surface appear to brighten and darken over time, as if ices are sublimating and recondensing in cryptic patterns. The contrast with other dwarf planets deepens the intrigue. Haumea, with its rapid spin and elongated shape, experiences seasons more like a wobbling top than a tilted globe, its irregular shape causing bizarre, lopsided temperature shifts. Makemake, lacking any known moons or atmospheric cycles, shows almost no seasonal variation at all, its surface locked in perpetual stasis. Eris occupies a middle ground, too distant for strong solar forcing, yet seemingly active enough to rewrite its surface over epochs. The wild card is Dysnomia. While Eris's axial tilt remains unknown, its moon's peculiar orbit could introduce gravitational nudges that mimic seasonal effects. Tidal flexing from their dance might generate microseasons subtle, localized heating that cracks the ice crust in rhythmic intervals, allowing fresh frost to well up in fractures. It's a far cry from Earth's spring blossoms, but on a world where change unfolds over generations, even these faint pulses could reshape the landscape in ways we've yet to imagine. Perhaps the most haunting possibility is that Eris's seasons aren't cyclical at all. Without atmospheric pressure to smooth out variations, its surface might evolve in fits and starts, long periods of stillness punctuated by sudden, irreversible shifts. A single century of slightly stronger solar radiation could trigger runaway sublimation, exposing darker bedrock that absorbs more heat and locks Eris into a new equilibrium. In this scenario, the dwarf planet wouldn't experience seasons so much as cosmic tipping points, each nudging it further from its original state. The mystery ultimately circles back to time. Eris's seasons unfold on scales longer than human civilization, their full pattern still hidden in the fragments of our fleeting observations. Until a probe makes the epic journey to its shores, we're left piecing together clues from flickers of light, watching a world where winter might last 1,000 years and spring could be a single, silent eruption of frost in the dark. Eris remains one of the solar system's most tantalizing lockboxes, a world crammed with mysteries yet with no keys in sight. Unlike Pluto, which yielded its secrets to New Horizons in 2015, or Mars, constantly swarmed by rovers and orbiters, Eris drifts untouched in the cosmic dark, its puzzles preserved by sheer distance. No missions are slated to visit it, no proposals funded, not even a concrete plan on the drawing board. This exploration gap isn't just a missed opportunity. It's a glaring blind spot in our quest to understand the outer solar system's most enigmatic dwarf planet. The challenges are daunting but not insurmountable. Reaching Eris would require a spacecraft with unprecedented speed and endurance. Current propulsion systems, even with gravity assists from Jupiter, would take decades to cover the nearly 7 billion miles separating us from this frozen world. A mission might need next-generation ion drives, nuclear propulsion, or solar sails capable of sustained acceleration technologies still in their infancy. Once there, the probe would face another hurdle. Eris's extreme distance from the Sun renders solar panels useless, necessitating bulky plutonium-powered batteries like those on New Horizons, but with even greater demands for longevity. Yet the scientific payoff would be revolutionary. To crack Eris's riddles, a probe would need an arsenal of specialized tools. A high-resolution camera could map its surface in detail, revealing whether bright patches are cryovolcanic deposits or exotic ice formations. A spectrometer might analyze the chemistry of its frost, pinpointing the strange compounds that defy radiation darkening. A magnetometer could settle debates about subsurface oceans by detecting faint electromagnetic signatures, while a thermal imager would hunt for the heat anomalies that hint at hidden geologic activity. Even a simple radio experiment measuring how signals bend around Eris could unveil whether it sporadically sprouts an atmosphere too thin for telescopes to spot. The absence of these answers leaves gaping holes in planetary science. Without direct measurements, we can't confirm if Eris's density stems from a massive rocky core or exotic high-pressure ices. We don't know whether its reflectivity comes from ongoing resurfacing or some unknown radiation-defying property. Even Dysnomia's origin remains speculative. Is it a collision fragment, a captured object, or evidence of a violent encounter with the hypothetical planet 9? Every unsolved question reverberates beyond Eris, affecting how we interpret other dwarf planets, Kuiper Belt formation, and even the early solar system's dynamics. The deeper irony, we're better equipped to study exoplanets light years away than this frozen neighbor. Telescopes like JWST can analyze the atmospheres of distant worlds, but Eris's lack of a substantial atmosphere makes it nearly invisible to such instruments. Its secrets are trapped in surface chemistry and subsurface structure, details only a dedicated mission could extract. Until then, we're left extrapolating from pixelated images and faint spectral lines, like trying to reconstruct a symphony by listening to a single note played through a wall. Some argue the cost outweighs the curiosity, but history shows that exploring outliers, worlds that defy categorization, often reshapes entire fields. Pluto's unexpected complexity forced us to rethink how small planets evolve. Europa's hidden ocean revolutionized astrobiology. Eris, with its contradictory traits and defiant mysteries, could be the next paradigm shifter. The question isn't just what we'd learn by going, it's what we're missing by staying away. And as long as Eris remains unexplored, a critical chapter in the solar system's story stays frustratingly, brilliantly blank. Eris's defiance of every expectation forces us to confront a humbling possibility. What if this strange world isn't the exception, but a signpost pointing toward undiscovered frontiers? For all its peculiarities, Eris might just be the first clue in a much larger cosmic mystery. The potential existence of other dwarf planets lurking in the Kuiper Belt's uncharted depths, each harboring secrets capable of reshaping planetary science yet again. Consider the patterns we've seen so far. Every time astronomers assume they've mapped the outer solar system's boundaries, another outlier emerges. Pluto was once considered unique until Eris appended that notion. Then Makemake and Haumea revealed themselves, each with their own oddities: Haumea's absurdly rapid spin, Makemake's complete lack of moons. Now Eris stands as the current record holder for dwarf planet eccentricities, but history suggests it's only holding that title until something even stranger is found. The math supports this hunch. Current surveys have only scrutinized about 20% of the Kuiper Belt's estimated territory, leaving vast swaths unexplored. At these distances, objects the size of Mars could still be hiding in the observational blind spots created by the Milky Way's star-dense regions or the ecliptic plane's dust. What makes this search urgent are the inconsistencies in Eris's own story. Its bizarre orbit, that dramatic 44-degree tilt, aligns suspiciously well with other extreme trans-Neptunian objects like Sedna and 2012 VP 113. Some researchers argue these patterns hint at gravitational influences from a massive, undiscovered world 10 times Earth's mass, the infamous Planet 9 hypothesis. While controversial, the theory gains credence from Eris's defiance of conventional formation models. If such a planet exists, it wouldn't just explain orbital anomalies. It could imply an entire unseen family of dwarf planets shepherded into peculiar paths by its gravitational sway. Picture a cosmic game of billiards where invisible players rearrange the solar system's outer reaches in ways we're only beginning to glimpse. Then there's the matter of composition. Eris's baffling reflectivity and methane retention suggest chemistry at work that our current models don't account for. If similar processes occur elsewhere, other highly reflective worlds might be camouflaged against the starry backdrop, their icy surfaces bouncing sunlight away too efficiently for our telescopes to catch. Or perhaps Eris represents an entirely new class of object, one formed under conditions so rare we've yet to spot another example. The implications ripple outward. If Eris-like worlds prove common, we'd need to revise how volatile substances behave in extreme cold. If they're singular, we'd have to explain why this one world breaks all the rules. The most tantalizing possibility is that Eris isn't even the solar system's final word on dwarf planets. Beyond the Kuiper Belt lies the hypothetical Oort cloud, a spherical shell of icy debris extending nearly a light year into space. Gravitational models suggest it could harbor super-Earths ejected during the solar system's violent infancy, worlds larger than Eris but smaller than Neptune, frozen in exile. Some might still bear the heat of their formation, sporting subsurface oceans kept liquid by radioactive decay or tidal flexing. Others could be composed of materials we've never encountered, forged in the primordial chaos before the planets settled into their current orbits. Eris's greatest lesson might be that we've underestimated the outer solar system's diversity. For centuries, astronomers pictured the realm beyond Neptune as a monotonous graveyard of icy fossils. Now we know it's a dynamic frontier where worlds gleam with unnatural brightness, spin at impossible speeds, and follow paths that defy prediction. Whether Eris remains a solitary oddity or the first of many such enigmas, its very existence proves one thing: the cosmos still holds surprises vast enough to humble us if only we dare to keep looking. And somewhere in that darkness, the next revolution in planetary science may already be drifting, waiting for its moment to shake our understanding once more. From its glittering, unexplained brightness to the gravitational whispers hinting at hidden depths, Eris has spent this entire journey defying every assumption we've thrown at it. 25 mysteries deep, and we've barely scratched the frozen surface of this cosmic enigma. Think about it, we've got a world that shouldn't be this reflective, yet somehow outshines freshly fallen snow. A moon whose orbit looks like it was drawn by a tipsy astronomer. Temperature anomalies that suggest underground heat on a body that should be colder than deep space. And let's not forget the granddaddy of them all, a density so high it's rewriting the rulebook on how dwarf planets form. Yet for all these paradoxes, here's the humbling truth: we're still seeing Eris through a keyhole. Every answer we think we've found just leads to 3 new questions. That's what makes this distant world so thrilling. Unlike Mars or even Pluto, where missions have given us definitive answers, Eris remains a blank canvas of possibilities. Is it hiding subsurface oceans? Could its crazy orbit point to unseen planets lurking beyond? Does that unnerving brightness come from processes we haven't even imagined yet? The fact that we're still debating these basics proves how much groundbreaking science is waiting out there in the dark. And that's exactly why Eris deserves our attention. In an era where space probes are visiting asteroids and drilling into Martian rocks, this dwarf planet sits like the solar system's last great frontier, a reminder that some of the most profound discoveries might not be light years away, but right in our own cosmic backyard. Future missions could revolutionize planetary science overnight, turning today's wild speculations into tomorrow's textbooks. Imagine a probe revealing cryovolcanoes taller than Everest, or confirming that Eris's core is made of materials we've never seen. Heck, even finding a single unexpected molecule in its ice could rewrite what we know about how life's ingredients spread through the cosmos. So here's where you come in. Which of these 25 mysteries stuck with you the most? Are you team underground ocean, or do you think Dysnomia's bizarre orbit holds the key to everything? Maybe you've got a theory we haven't even covered, something that could explain why Eris refuses to play by the rules. Drop your thoughts in the comments. Some of the best scientific ideas start as casual conversations. And if cosmic enigmas like this get your brain buzzing, hit that subscribe button, because the universe, it's packed with puzzles way stranger than fiction, and we're just getting started. One thing's certain, Eris isn't done surprising us. Every flicker of new data, every pixel from future telescopes could be the clue that cracks this case wide open. Until then, it'll keep spinning out there in the frozen dark, a glittering riddle daring us to come find the answers.